about a decade ago, we developed a new technology called brain-machine interface to test a few theories on how the brain actually operates. It's almost like building a little CERN. Instead of studying particle physics, we decided to study how populations of neurons work to produce motion. And what you see there is the diagram that came out of these experiments where we could actually sample these electrical storms, these brain storms in real time, extract the motor commands that were generated by a brain, and in less than a half a second, send these commands now in digital form to a robotic device that could actually generate the movements that that brain was planning to do even before the actual body of the subject moves. So that subject just needed to think about what it wanted to move, and the robot device would reproduce the movement needed and execute the behavior that was required for that animal to get a reward. So I'm going to show you a few experiments that show you how we start in this last decade, as I said, liberating the will of the brain way beyond the limits of a physical body. And that started with primate studies at Duke that basically allowed us to actually start dreaming with this scenario in the next decade. So if you have here, in the left part of the image, a patient that suffered a spinal cord lesion, what we have discovered in the last 20 years is that the brain continues to imagine all the movements that this patient would like to perform. But these brain signals, these electrical signals, because of the interruption of this highway that's called the spinal cord that carries these signals to the muscles, because of this interruption, the signals that are generated here can no longer reach the muscles, so the patients are paralyzed. What we discovered over the last decade is that there is a possibility, using these brain-machine interfaces, of creating bypasses that will read these signals produced in the brain, bypass the lesion, and send these through a series of devices to a robotic vest, a whole-body robotic vest that will be controlled by the brain alone and will allow these patients to actually restore their motor behaviors that they have lost due to this lesion. And the way we got there is basically in experiments like this. We have primates that were trained to play with joysticks and play video games in our laboratories, and as they played, we record the brainstorms produced in their brains, and we extracted, using a series of computational methods, the motor programs, the motor commands that their brains were producing. These programs were then delivered to a robotic device that, like a young child, was learning to move according to the commands produced by a brain. Well, after a few weeks of training, we did a trick in our monkeys, as you're going to see in the video clips. We actually turned off the joystick, removed the joystick from the game, and now for the animal to play the game, and you'll see how they play, and to acquire the result of the game, that is a juice reward, a drop of orange juice that they love to get every time they play the game correct. What they have to do now was not anymore to move a joystick, to move a computer cursor and acquire a target on the screen. They now had just to relax, not move at all, and imagine the movements they need to make to acquire that target. And what happened was, as you were going to see, the robot actually did the movement needed for the animal to move the cursor, get the target, and drink the orange juice that they crave so much. So this is a brain-machine interface at work. So this is our first historical subject, Aurora, who was using a joystick, as you can see, to play the game. And as a good primate, she has to move this cursor inside the target that appears in random locations every time. And every time she does that, she gets a drop of orange juice. As a good primate, she's trying to cheat before the target appears, as you can see. It doesn't work because it's random, but they still try it. And every time she crosses that target, she gets a reward. You can see that she's making very precise movements of this joystick like one of our kids. And is playing at 98% correct. So she's drinking about 360 ml of orange juice a day just to play this game. So I'm going to show you what happens when, after the programs that we designed acquired the brain patterns that the Aurora was producing to play the game, and was successfully able to send these patterns to a robotic device, how Aurora continued to play this game. 3 minutes later, the same day, 10 years ago, that's what happened. You can see Aurora moving the cursor. She's acquiring the target as you saw in the previous clip, but there's no movement. There's no body movement whatsoever because she really realized that there's no need for that. There is now a surrogate arm, a robotic device that's actually doing the movement for her, and you're going to see that arm in a minute in a different room, that is basically taking the brain activity that Aurora produces to plan these movements and actually does the job for her. So in about 10 minutes, she realized after 4 weeks of training that there was no point whatsoever to move her biological body. Her brain activity had been liberated from the physical limits of that body. She could now control a third arm, a robotic arm, that is actually 30 days later doing the job for her. She's actually moving this robotic arm just by thinking. The robotic arm is controlling the movements of the cursor, and the cursor is acquiring the target that gives her the reward. With one difference here, 30 days later, she realized that she now literally has 3 arms. She can play the video game with the robotic arm just by thinking, but she can use her biological arms to do other stuff that monkeys like to do. Scratch her back, scratch a scientist walking around, and grab more food. So she basically has assimilated the robotic arm as an extension of her biological body. In fact, in the last couple of years, this international consortium called the Walk Again Project that involves universities here in the United States, in Europe, and in Brazil, are actually trying to take this to the limit and build the first exoskeleton that will be used, a whole body robotic vest that is going to be used to restore full body mobility in patients that are either quadriplegic from the neck down or paraplegic from the hip down. And this thing is being built as joint by joint so that not only the brain of the patient, the brain activity of the patient can control the mobility of these joints, but the entire exoskeleton is going to be sensorized so that tactile feedback can be sent back to the brain as the patients take advantage of this. So at this point, we are trying to be ready for the opening ceremony of the World Cup, the Soccer World Cup in 2014 in Brazil, because our dream is to have a young Brazilian teenager that is quadriplegic or paraplegic walk in the field in the first game of the Brazilian national team and be responsible for the opening kick of the World Cup.